So the next thing is, it's kind of trivial, you'll understand it. You could have worked it out yourself. Many people have worked it out. But it turns out that two field medalists, both of them brilliant geometers, one called Milner and the other one called Thurston, worked it out, and it's beautiful and simple and intuitive. And it totally solves the problem of all admissible orbits in unimodal maps. So maps that stretch and fold the unit integral back into itself. So that problem is totally solved. That's about the only problem in dynamics in which the relation between symbolic dynamics and time evolution is totally clarified. So you can go between one and the other freely. It's called kneading theory because what these maps are, they are really ways of making Danish pastry. You stretch something, you fold it, you stretch it again, you fold it. That's what this map means. It's just infinitely thin pastry, but you keep folding it and stretching it in a simple linear way. And it's true for any map, any unimodal map. One exercise in a book that you are invited to do was done by the mother of hydrogen bombs, Stanislav Ulam, at Los Alamos. He showed that the 10th map is conjugate, meaning that there is a transformation, G, where you take the 10th map and then go back to original coordinates, just the way we are changing by nonlinear transformation. And you get F. And this is parabola. And this is 10th map, complete 10th map. That's crucial. And this conjugacy is good every place on the interval, excluding the left fixed point. So it's good on 0 to 1. Left point is excluded, is very important. The conjugacy is not complete. There is a conjugacy. The reason I don't want to do this exercise is because it's the usual thing about mathematics. We can do it. It happens only once in your lifetime and you're done. Generally, we don't have maps which take a smooth map in dynamical system and produce a piecewise linear smooth map. That's expecting too much of life. So the conjugacies are topological, meaning that these functions exist. You can construct them, but they are ugly functions which are no place differentiable. There's only one example which I refuse to do on the blackboard because you can just do it yourself. You have to do it just to understand it can be done, and this is the only time it'll ever be done. It's so very hard to find conjugacy. So I'm not a big fan of actually constructing this conjugacy function because you have some dynamical system which is smooth, like a known map, Rossler. And you can try to make this thing look like two flat things, but you pay a huge price in this conjugacy map not being any place differentiable and nice, etc. So it's just not worth your time. But that means topological conjugacy. For us, it will have very simple geometric meaning. It's a map that preserves the ordering of points on a unit interval. So if you sense that somebody is to the left of somebody else, after topological conjugacy, this is still true. So it preserves ordering, but nothing else. All the distances change in not any nice way. Ulam did one explicit calculation in which he turned parabola into a 10th map. One parabola to 1/10th map. If you try to do it for any other parabola, it doesn't work. There is one parabola which is called Ulam map, which is a parabola that has topologically looks similar to this because it's a map which has a critical point at whose value is exactly 1. So it's a unimodal map that stretches the half interval over the whole interval. Ulam cannot do it, or nobody can do it if you take another map. If you try to take any other parabola or any other unimodal map, you will fail. I don't know of any other example. In Ulam case, G is smooth. In general, you can claim that there is a map, but if you try to construct it, you'll find it horrible. The whole point is simply to say, it might seem that while we're looking at linear, discontinuous, or non-differentiable linear maps of unit interval, there is a good reason. And here is the amazing thing that we now get out of this. We can now generalize this map a little bit to a map I'll call Dike map. It's still piecewise linear, so it's obviously something that's doable. What I'll do is I'll cut it and say, I have a mapping, but now I have 3 intervals down here. I have an interval, I'll call it gamma critical. So now gamma critical has become a whole line. It used to be just a point. But that line returns a single value, just like this one. And then I have my left part and my right part. Now in practice, I will not discuss 3-disk in this class because it's so easy, but I've done it in videos, so look at them. And the videos are so easy of 3-disk system because you can think of this part as being a whole and everything escapes, and then you're just looking at dynamics of things that survive. Or you can think of it as approximation to top of parabola, where you make very flat parabola at the top, saying that everybody in this interval, maps to a very small neighborhood. Either way will work. And now what happens is, and you see it in front of your very own eyes right now, I used to have a beautiful 2-cycle, but this map doesn't like it because, the branch doesn't go there. It has this value, but this will never close in a 2-cycle. So what has happened is that of all these sequences I could just write down, I could tell you where everybody is. Suddenly, I realize that there are some sequences that I can never get. What are those sequences? We define this value here, a number. We define it as kappa. K shows up for word kneading in English, which is the value of my function. This is kneading sequence. So now I take my value of my critical point, this thing here, and I compute this kneading sequence. What is that? I just start with it and I run around and keep recording zeros and ones. And that's kind of the highest possible position in space that I can find, because anything that's higher than it has been pruned, cut, removed, forbidden, verboten, not admissible. So I compute the kneading sequence of this final point, and when I convert that kneading sequence back into kappa, I get something called kneading value. Now I compute its sequence, and that's a position that's kappa. That's something I compute just by iterating my system forward and marking where I am. And then from that kappa, I can compute the kneading value, which is actually position in state space. And it has a property that, now here is the punchline, so if you get this, we're in a good shape. It has a property that anything that's to the right of it in physical space, state space, this is pruned. Meaning, before I had a 2-cycle, but it had a point which was inside of this region. The map never gets there. It doesn't stretch hard enough. So this point is not allowed. It's allowed for a full tent map. So we have our list of points that are allowed. Our original list of orbits had all sequence zeros and ones. But if I get a point on the orbit which ends in this forbidden red region, then I don't have that sequence. So now we have answered the question, which is a very hard question. What are the admissible sequences? Meaning which sequences the system actually realizes. Because our partition, 0 and 1, allows us to write any sequence of symbol, right? But do we know whether such orbit actually exists? For unimodal maps, we do. So for unimodal maps, we can state it as a theorem. That's called admissibility. We would like to have a description of all time sequences, all motions which a given dynamical system allows or admits. Let K be the Kneading value. The way you'll find Kneading value for your Rosslare system, for example, you'll find the critical point, which will be the highest point of your map, and you'll just iterate it forward in time and get a sequence. And from that sequence, you'll be able to compute coordinate in this map, in the topological representation. So the original map, you might think of map of Atlanta, with roads going all over the place. And this map is a flattened and straightened map where they're all orthogonal to each other. We can use our physical system to compute the Kneading sequence, and then we can use our nice map, topological map, to compute the Kneading value on this topological map. Then define gamma coordinate in our idealized system, our piecewise linear Dijk map, of the future forward itinerary of our real system. So in real system, we take a point and we just run it. Or you might have a designer point. You might say, I would like to find 0, 1, 0, 1, 0, 1. And I compute from it, that's my future itinerary. So I take that. And now let it be maximal. What does that mean? If I have an orbit like this 2 cycle, I have a bunch of points on it. For each one of them, I can compute this gamma. Maximal is one that's furthest to the right. Periodic orbits will be easy because they are finitely specified. For normal number, you never know, because there could be next step that puts you outside. So you only can think of it as a limiting thing. So that means it's supremum m over take your forward itinerary S plus, and then apply to it any number of shifts. Because in symbolic dynamics, time evolution is just a shift, meaning you go to the next digit, and then for every next digit you evaluate again using this rule where you are in a physical space. Then orbit with topological itinerary S plus is admissible if and only if the supremum is to the left of the Kneading value. This is now wonderful. You produce a list of orbits you think they believe before going to a computer trying to find them. You run them through this test. This test is only done on level on symbolic dynamics. And you throw out everybody who is pruned, who is inadmissible. The rest you put in computer and you nail them down for your flow. If you pick out a normal initial condition, you just close your eyes and you put your finger with angstrom sharp nail on it on the unit interval and let your system run. With probability 1, this will be inadmissible. Because what admissible is a finite interval. It's been cut out and all its pre-images, everybody who lands into it. So the remainder is a fractal set. So actually the set of admissible orbits is totally non-trivial, but in this particular case we have a criterion. So if you want to do your calculation and you want to find all orbits to length 120, because that gives you some precision in some prediction for something that we will study in the second part of the course, how do you do this. In this case, and in its generalization, which is not rigorous by myself, called pruning fronts in 2 dimensions, we can specify all orbits that exist, and then we know what we are doing. In this case, I know, and it's the usual thing. This kappa sets, itself takes values on some kind of fractal set, because you're pruning fractal sets as you change the top of your map, etc. And for that guy, for every value of that, I can give it specify to any precision you wish. What subset of possible conceivable orbits is realized by this dynamical system. And you can, plot nice fractal pictures if it makes you happy. If you start with symbolic dynamics, so if you hand tailor an itinerary, gamma hat says that in your topological map, you will be moving someplace, and gamma hat is as far right as you ever got on this orbit. Supremum of. Next step is you have to check, is this supremum to the left or right of your kappa value? Because symbolic dynamics are picked for the full tent map. They're saying everything is allowed. And now you're dividing in 2 sets, the ones which are allowed by a Dike map, which is less vigorously stretching in the original map. Doesn't cover the whole unit. It's very easy to understand it in the map of Manhattan because it's organized. This topological representation is really nice for anything that has binary covering dynamics.